One of the astounding discoveries in astronomy in the 20th century was the fact that if we look at a galaxy and we look at the Doppler shifts from stars from the inside to the outside, we find that the rotational speed around the center of the galaxy for stars does not diminish that much. Uh, in a solar system situation, you would expect by Newtonian physics, Mercury would be the fastest planet around the sun, and through a inverse square root relationship, you would expect that speed to diminish as you headed out towards Neptune and Pluto. The early astronomers that were working with galaxies were kind of suspecting the same things when they were looking out from the center, but they eventually discovered that the speeds did not diminish that much, and that kind of led to the theoretical existence of dark matter. When we use our radio horn telescopes, we'll see a variety of different Doppler shifts at different places in our galaxy. So I wanted to create this computer simulation to kind of see what rotation patterns would look like if everything was moving the same speed. So every colored ball in this simulation will move at the same speed and orbiting around the center of the galaxy picture. And you'll see that the sun is a distinctly different shaped yellow star right here, and we'll be able to switch perspectives from the galactic center to the sun-centered universe. So I'm just going to let this run right now. So hit the run button. And so once again, everything is moving the same speed. It's just that the inner lane, the red stars, have a shorter path, so it seems like they might be moving faster. So if I look at the sun, I can see it's moving away from blue. The green is moving away from it. And here comes an orange that's actually catching up to us. So that's going to lead to different Doppler shifts. Right now I'm just going to let it run for about a minute so we can see what's going on. What I'm going to do now is I'm just going to take I'm going to stop it for a second, and I'm going to remove the background star. So I'm going to just have to reset this. I'm just going to take that picture off. Because the program is dragging that picture, it runs a lot slower, so this should run quicker just to see that dynamic. You can see the sun, you can see some stars catching up to it, some stars moving away from it. This would lead to Doppler shifts of red and blue that we would see as we look through the band of the Milky Way with our radio horn telescope. So the nature of the simulation and its regularity sometimes means that the stars kind of line up in very regular looking patterns, but for the most part it seems kind of random. So what I'm going to do right now is I'm going to shift to a sun-centered version. I'm going to stop it, and I'm going to reset, and I'm going to bring that picture back in so I can see this. And I'll just start by running it. So once again, the inner things, pretty much everything seems to be moving away from us at this point. One thing that we can get out of the galaxy picture is the quadrants, the galactic quadrants that we see when we look out into the Milky Way. I'm going to switch this to a sun view in a second so we can see what happens here. So right now the point of view is with the sun, so we don't see the sun motion. But what we do is we see the inner things seem to be completing their laps faster, so they appear to be moving kind of, in this case, clockwise, whereas the outer lanes, the ones that are further away from the center of the galaxy than the sun is, seem to be moving in the opposite direction. So if we were looking in this direction with a telescope from the sun, we would see some things that are moving away from us, some things that are moving towards us, and in the case of the yellow star that's in the same lane as us, it doesn't appear to be moving at all. And we would see all of those Doppler shifts in, uh, in the actual data taken with the radio telescopes. So once again, I'm just going to kind of let this sit and run for a bit in case you wanted to use the simulation, have the kids kind of pick some information out. Just a reminder that in galactic coordinates, the zero longitude is going to be towards the center, out towards 90 degrees, as is represented in this graphic, is the first quadrant. So I can look into the first quadrant, I see some things that are moving away from us, some things that appear to be getting closer to us. When we get into the second quadrant down here, the few stars that are out there seem to only be coming towards us. This is getting a little bit closer, this distance. When blue comes in, it's going to be closer. So we would expect to see some fairly significant blue shifts only in this quadrant as we look in that direction. So if I had my Horn telescope and I moved out towards about 90 degrees longitude, then I would see a lot of blue shifted signatures from the hydrogen, the neutral hydrogen lines that we would see. In the third quadrant, which is highly visible in the southern hemisphere, we'd see things moving away from us. And in the fourth quadrant, we'd see a mixed bag again. As we look towards the center, we see stuff coming towards us. That would be blue shifted. We'd see stuff moving away from us. That would be red shifted. So this would be more, this particular setting right here would be more in tune with what we would see because we don't feel the sun is moving when it really is. So when we look at the other things in motion around the galaxy, this would kind of explain that and help us kind of visualize and understand the shifting Doppler effect values we get out of these radio spectrum for the neutral hydrogen. So hopefully you can utilize this video and run through it back and forth with the different perspectives with and without the background of the galaxy, and use it to have the kids work through some ideas and visualizing the way things move in a galaxy.